Hi everyone. This is the last session of today, and the first talk is going to be given by Huangjun Zhu. He will talk about the magic in Qudit shadow estimation based on the Clifford group. Please.
Okay, thanks for the introduction, and thanks for the organizer for giving me this opportunity to talk about our recent work about the magic in Qudit shadow estimation based on the Clifford group. So here is the outline. So we start with the introduction to shadow estimation. So in quantum information processing, it is very important to characterize and verify large quantum systems. But with traditional tomography, the resources required would increase exponentially with the system size, which is too prohibitive for practical application. So shadow estimation was a powerful tool introduced recently to circumvent the curse of dimensionality. So the basic idea is very simple. So basically, you perform randomly pick a unitary transformation from a given unit assembler. Then you perform computational basis measurements. Then you process the data obtained, and then you can construct estimator for many observers of interest. So here's the basic procedure, as I mentioned. So the idea is very simple. So now the question is, how efficient can this protocol be? So it turns out this protocol's efficiency is determined by what is called the shadow norm. So the shadow norm will depend on the observer and also on the measurement unitary ensemble that you choose. So in the worst case, this shadow norm is minimized when the ensemble form a 3D design that I will introduce later. For example, the Clifford group form a 3D design. In particular, for fidelity estimation, the shadow norm does not depend on the system size when the ensemble form a 3D design. So this is as efficient as we can expect. Okay, now a brief introduction about Clifford group and T-design. So Clifford group is one of the most important groups in quantum information processing. So here we are interested in this group because its connection with shadow estimation and T-design. So so in particular, it's known there is a Clifford group forms 3D design in the Qubit case, but the situation different in the Qudit case when the local dimension is larger than 2. Okay, so here's introduction about the Clifford group. So mathematically, let's start with very simple, this Pauli group. So everyone should be familiar. So Clifford group is defined as a normalizer of this Pauli group. So this definition is very simple. Also, the Clifford group can be generated by very simple gates like head-mount gates, phase gates, and control NOT gates. Also, it's known that Clifford circuits can be simulated efficiently by a classical computer according to the Gauss-Meinel theorem. So this property is also very useful to shadow estimation. And if we can add T-gates, then we can realize universal quantum computation. So now we generalize this group to the Qudit setting. In the Qudit setting, so the analog of Pauli group is known as the Heisenberg-Wei group, also known as generalized Pauli group. So this group is generated by this phase operator and cyclic shift operator defined in this way. Also very simple definition. Then the Clifford group is also the normalizer of this Heisenberg-Wei group. So this is very similar to the Qubit case. Okay, next we have a very brief introduction about T-design. So in many applications, we quite often require random states or random unitary, but it's known that hard random unitary states are very difficult to implement. So T-design are introduced to reduce this difficulty. They are easy to sample, but in many cases can replace hard random states or unitary. So they have many applications, in particular in shadow estimation, that is focus of this talk. So this is formal definition. So basically, ensemble of quantum states T-design if the moment operator is proportional to the projection to the semi-subspace, or equivalently if it can reproduce the first T moments of the hard random states. Similarly, for unit ensembler, it is a T-design if the Tyrolean operation is identical to its counterpart based on the Clifford group. So it knows that for any t, t can be constructed, but if you require t is larger than 2, larger than 3, then t with simple structure are quite rare. So here are some examples of compact projective design in the case of qubit represented by platonic solids on the Bohr sphere. So now let's focus on the distinction between the qubit Clifford group and the Qudit Clifford group. So about 10 years ago, Zach Weber and I proved independently this result. So basically, the Clifford group in the case of qubit is a unitary 3 design. But in the case of Qudit, when local dimension is order prime, the Clifford group is only a 2 design, but not 3 design. As a consequence, any orbital of the qubit Clifford group from a complex projective 3 design. So this result has a profound implication for schedule estimation. In particular, this means schedule estimation based on the qubit Clifford group is maximally efficient for important tasks like fidelity estimation. So now how about Qudit? Because the Qudit Clifford group is not a 3 design, so what can we say about the schedule norm? So this turns out to be a difficult problem because the previous tool cannot be used to solve this problem. So after 2 years of study, eventually we settled this problem. So another question is, can we achieve similar efficiency in Qudit schedule estimation based on Clifford group as in the qubit setting? So according to our results, the answer turns out to be positive. Okay, so here's our main result about schedule estimation based on the Qudit Clifford group. So we provide a very simple and nearly tight upbound for the schedule norm, which is independent of the Qudit number. So this result means in Qudit schedule estimation based on the Clifford group, we can achieve similar efficiency as in the qubit setting, except for a very small overhead that depends on the local dimension. So in particular, when d is equal to 2, then we get back the result for the qubit case. So in the case of stabilized states, in particular in the case of fidelity estimation, so we can even derive an analytic formula for this schedule norm. And this norm actually almost saturates the bound presented in the previous slide. So now next question is, can we further eliminate the dependence on the local dimension? So the answer is, again, positive. And this can be achieved by a very simple modification to the Clifford circuit. So basically, we can add just a single layer of major gates in the Qudit setting, also called T-gates. So with this modification, we can achieve the same efficiency as in the qubit setting. So here's our main result about this schedule estimation based on this modified Clifford circuit. So as you can see, the schedule norm is bounded by this number gamma dk. So this, if you need just one T-gate, then this bound is independent of the local dimension and also the qubit number. And if you add more T-gates, then the deviation from the qubit case decreases exponentially with the number of T-gates. So here's a plot about this schedule norm of stabilized states that is relevant to fidelity estimation. So you can say if there's no T-gates, then the schedule norm increases approximately linearly with local dimension, but it's almost independent of the qubit number. And if you add one T-gate, then we can get a universal upbound with the schedule norm. So this is another plot that we have more T-gates, then the schedule norm decreases exponentially, eventually approach the counterpart in the qubit case. Here's some result about schedule norm of random observable. So in the case of completely random observable, the schedule norm is actually quite concentrated in the, so the average behavior is similar to the qubit case. But if you focus on diagonal observable, then the schedule norm is larger. almost increase linearly with the local dimension, but it's independent of the Qudit number. So here are some numerical simulation results on Fidel estimation of GHZ states. So to this end, actually, we proposed a simple algorithm that generalizes the previous algorithm that applies to the Qudit case. So our approach is very efficient, can simulate this Fidel estimation for more than 100 qubits. So you can say that if we use one or two T-gates, then the result is almost independent of the local dimension. So we achieve similar efficiency as in the Qudit case. So this is another plot based on about Fidel estimation of depolarized GHZ states. Okay, so next we discuss briefly about the mathematical foundation of this result. So the full proof is quite lengthy, but we will condense the full more than 100-page of proof, just condensing this one simple slide to provide very simple high-level ideas. So basically, we notice that the shared norm for Fidel estimation or shared estimation is determined by the moment operator of a certain Clifford orbit. And this moment operator belongs to the commutant of the Clifford group. So the dimension of this commutant previously, about 10 years ago, we have already determined this dimension of the commutant and given by this very simple formula. And recently, in a similar paper, Gloss, Nesami, and Walter further constructed a basis for this commutant. And their construction is based on what is called stochastic Lagrange subspaces. So in this way, they established a sure wave derivative for the Clifford group that is analogous to the more familiar sure wave derivative for the 4 unitary group. So this result is very elegant and very powerful. And based on this result, we can prove that because the moment operator is a linear combination of these basis elements, then we can prove a very simple upbound for the contribution of each basis element to shared norm. In this way, eventually we can clarify the simple complexity of Qudit shared estimation based on the Clifford group. Okay, so next I will discuss briefly about another quite related problem known as Swift shared estimation or multi-shot shared estimation. So for simplicity, we just focus on the Qudit case. So here's a motivation. So in the original protocol shared estimation, every round we pick a new random unitary and apply. But this is not so friendly to experimental implementation because we have to adjust the experimental setting very often. So now here's a very simple alternative. For each random unitary, we can reuse many times. So now the question is, whether this reusing circuits is really useful. Can we, in this way, save the number of random unitaries that we have to choose? So the answer turns out it depends. Depends on several factors. For example, in particular, the underlying unit ensemble that you choose. Actually, this problem has been studied by several groups previously. So previously, they found that reusing circuits is maximally effective if the underlying ensemble is a full design, for example, hard random unitary. But it's not so useful if the ensemble is a Clifford group. But this result is a bit unfortunate. Because the Clifford group is the most simple, most useful group in quantum information processing. So we are interested in ways that we can use Clifford group to realize the efficient Swift shared estimation. So the answer actually turns out is also positive. So we notice that in the Swift shared estimation, the variance can be expressed as a linear combination of 2 terms. So here the first term is the variance in original shared estimation. The second term, phi star, is related to the multi-shot Swift shared estimation. So now from this formula, it's clear that silver-shielded estimation is effective when this phi star is much smaller than phi, the contribution in the original shielded estimation. So now to clarify the effectiveness of shielded estimation, we need to clarify the property of this term phi star. So here's the result about the variance in the original shielded estimation just as a benchmark. So basically, this is about are bounded by 3 times with 2 norm. So now suppose we can perform shielded estimation based on full design, then we can have very simple upper bound for this term phi star. So this is from this result we say that this is much smaller compared with another term phi. So this means if we use the full design for shielded estimation, then this is very effective. But how about the Clifford group? So this is more practical. So then it turns out it relates to a very important resource measure called stabilizer 2 linear entropy. So this is a resource measure in the resource area for magic state quantum computation. And stabilizer 2 linear entropy is very appealing because it is very easy to compute, and you do not require sophisticated optimization. Okay, so now come to our main result about silver-shielded estimation. So we give a very simple bound for this phi star, this variance in silver-shielded estimation. It turns out this variance decreases exponentially with stabilizer 2 linear entropy. This means for Philly estimation, those states with high stabilizer 2 linear entropy, usually this means states that are more complex. But surprisingly, and also fortunately, such states can be estimated more efficiently compared with stabilizer states. Because most states, they have a very large stabilizer 2 linear entropy, so our result means most states, their fidelity can be estimated efficiently based on silver-shielded estimation. So this is a result about average variance. Furthermore, if we can add 1 layer of T-gates, then we can further reduce the variance and increase the efficiency. So here our main result, another result. So I prove that basically the magical non-stability in states and in the unit ensemble can constructively help reduce the variance. In particular, the variance decreases exponentially with the number of T-gates. So here are some plots that confirm our theoretical prediction. Also, very surprisingly, this variance usually decreases monotonic with the dimension of this system. So this is very useful to practical application because we can use few resources to estimate a system with even larger dimension with more qubits. So here another plot that conveys the same phenomena. Okay, so now comes to the summary. So we showed that the Qudit shielded estimation can achieve similar efficiencies in the qubit setting, although the Clifford group in the qubit setting is not a 3D design. Moreover, a single T-gate can bridge the gap between the qubit setting and the qubit setting. So our result means qubit system can be characterized and verified much more efficiently as expected previously. Also, we showed that silver shielded estimation is much more effective than expected. And the variance in silver shielded estimation decreases exponentially with stabilizer 2 linear entropy. In this way, we also provide the first operational interpretation of this stabilizer 2 linear entropy that is appealing to the resource theory of magic quantum state computation. Okay, that's all. Thank you. Thanks.
Any questions?
Hi, thank you for the very interesting talk. I'm curious, for the Qudit Clifford gate and T-gate, is there a way to efficiently sample from that? like?
Yes. So they can sample it very efficiently as in the Qubit case.
And also another question, what does the Qudit T-gate looks like?
Actually, there are many different kinds of T-gates. They are determined by Qubit polynomial. We have a very explicit expression.
Thank you.
Thanks.
Are there other questions? I think we have plenty of time. Okay, so if there's no other question, we will take a break, and I think our next talk starts at 4. And can the next speaker come up to the stage and get ready? Thank you.
All right, thanks.